So this is some work. It has actually a pretty interesting history. This work was started last year in Hobart. Dave Airley and I were sitting out in the sunshine, enjoying the sailboats in the harbor there, and talking about what we should do about connecting virtual reality devices to a Linux system. And we came up with a bunch of crazy schemes, and I'll go through those. And I got a little sunburned, and I enjoyed the sunshine, and I think at the end of the hour we had actually come up with a plan, and we thought, oh, this will only take a couple of weeks to do. It's a really simple plan. Of course, I knew that in reality it would take a lot longer, and in fact we're just now starting to get the last of the bits of the code merged upstream. This is work sponsored by Valve. I'm a consultant for Valve at this point doing this work. They are building virtual reality systems. They have a bunch of games. You may have played some of them. It's interesting to take those games and think about how they might work in a virtual reality environment. Virtual reality environments have a bunch of different components. You can see them here on the screen. You have the traditional virtual reality headset, which blocks you off from reality, giving you only virtual reality. It's great if you want to stumble into walls, chairs, and tables. There are a couple of location beacons. The HTC VIVE beacons actually have a little rotating device in them, so they sit in your office and kind of hum quietly to themselves. They have a lot of cool LEDs inside, so they're kind of nice wall art. You're supposed to bolt them onto the wall and have them fixed in place. I, of course, stuck them on a shelf in my office. And then you have these crazy handsets that you're supposed to interact with the world in. They have a really accurate model of these so that when you're playing in the virtual reality environment, you can actually see the handsets, which is really creepy. I mean, you're sitting there, you have these goggles on, and the entire world is gone except for the handsets. And oh, I can find where those are. It's kind of fun. How many of you have played with virtual reality headsets? How many of you actually? Oh, everybody, okay. I appear to be the last person on the planet to ever even get one of these. The only reason I purchased one of these was because I was doing work to make them work, which is a pretty traditional way for me to get new hardware. Obviously, the headsets are interesting. They have to have an IMU in them, an inertial measurement unit, to actually know where they are in space at a very high resolution in time. They have to have a navigation interaction with these beacons to know where they are absolutely in time to reorient themselves. And then they have to have a display in them and some optics. So the display in this particular one is about 2K by 1K. And then it kind of splits that in half and it has a bunch of lenses. So they're kind of more complicated than you would hope in terms of actually using them. In the process of displaying the image, it actually goes through a bunch of computation. So the left eye buffer, the right eye buffer are computed separately by the application and put into a unified frame buffer. Eventually. They have to go through an optical transformation. There are optics, lenses in the headset that distort the image. And in order for you to see the world in a reasonable facsimile of what you want to see, you have to back out that transformation. And then you have to take the fact that this is an OLED display. And in an OLED display, every single pixel of the OLED display has a slightly different intensity. It's not really noticeable on your phones because the phone has a fairly static image on it. Or when it's animated, you're expecting to see things change. In a head-mounted display, when you have a static image, which is to say an image of the world, and you move your head, the image of the world moves across the field of the display. And so even though you're viewing what is perceptually a static image, on the display you're re-rendering it all the time and recomputing all these transformations, putting the resulting image in different pixels. And that means this optical intensity variation that's inherent in OLED displays is really, really visible and a terrible artifact. And it kind of breaks that the illusion that you're looking at something fixed in space. So the HTC VIVE actually has in the hardware, it actually has a map of the pixel intensity of every pixel on the screen. And so when you're presenting the image to the screen, it actually backs out that transformation and adjusts the intensity of every pixel on the screen to counteract this variance in the OLED display. And then once you've got all that backed out, you can actually send the image to display and get it presented to the user. So there's actually a bunch of computation. One of the important things you need to understand here is if I just take my regular Linux desktop and dump it into this frame buffer, it's not going to be useful. So this display is inherently not a part of your desktop environment natively. Now obviously I can take the images of the environment, and construct a projection of those into this environment and give yourself a desktop here. But your existing Windows system isn't going to be able to use this device as an output, directly as an output. One of the other interesting parts about head-mounted displays is they are probably the most hard real-time we have on the desktop. We think about trying to make sure your mouse interactions are smooth and the cursor follows your mouse. But when the cursor fails to follow your mouse and kind of jerks across the screen, it's like, yeah, I don't really feel like my hand is connected to the mouse, and it's annoying. When the scene in front of your face doesn't track your head motions correctly, you get violently ill. Right? This is a real problem, to the point where a lot of the people that I interact with who are, of my age, really cannot use these devices often cannot use these devices because it provides this perceptual very disorienting perceptual experience where you get even the slightest latency between a head motion and the reprojection of the scene into that moved environment. So we really have to get the times nailed. Every single frame has to be displayed not only correctly in terms of what the pixel content is, but correctly in terms of time. So we've taken a two-dimensional, make sure the scene is correct problem that we've been working on to get rid of tearing on environments in our games for the last 30 years. And now we have a three-dimensional thing where we're adding this dimension of time. The slowest that the human factors people tell us we can go with a head-mounted display is about 90 frames a second. Now that's 50% faster than your typical display. We cannot miss frames. We absolutely have to hit every frame. Of course, because you're playing a game or looking at some other environment, the geometry and the textures and all the data necessary to construct that image vary for every frame. Right? Every frame is going to be a little bit different. As I said before, it's definitely not part of the desktop. You can't just present an image in this frame buffer. Just presenting a static image, which is one of the little demos that I would love to be able to run, but I don't have the head-mounted display with me. Just presenting a static image is really hard because now you have to track the user's head and make sure that that image is displayed correctly so that the user sees that image as if it were static in the world and not static on the display. In debugging this, I often get a static image in the display. And let me tell you, when you're all of a sudden your 3D image freezes and it stops moving when you move your head, if you don't hold your head still, you're going to fall over. Because you don't understand just how tightly coupled your vestibular system and your visual system are in terms of getting feedback about the orientation of your body. I sit down when I'm doing development of this system, and I have fallen out of my chair several times. Yeah, it's like, wait a minute, is this going to work? Okay, I'm sorry for the eye chart here. So when Dave and I were sitting outside enjoying the harbor in Hobart last year, we talked about a bunch of different possible ways of getting HMD displays integrated, head-mounted displays integrated into the Linux desktop. One easy way would just be to have some conventions to hide the displays from regular applications. It's like, okay, so your head-mounted display application can just tell the system, yeah, that display, don't let other let's develop some conventions and then we'll go change all the desktops so that they know about the conventions, and that display will just be hidden from the desktop. The rest of the system would be exactly the same. We'd have an X Windows system sitting there. It would be part of the frame buffer. You'd have the regular DRM interactions with the kernel, so we wouldn't have to change anything, any of the system software. We'd just have to change every desktop environment on the planet. Some of the real reason that other than, oh my God, I have to go fix KDE and GNOME, the other real problem, of course, is that we have tremendous latency problems with talking to the Windows system. The Windows system is not a hard real-time environment. It really is like, well, kind of a best effort. You give me a frame and yeah, I'll put it up on the screen sometime. Especially when you start talking about a compositing desktop environment, where all of a sudden you're taking the images from multiple applications and blending them together and putting that on the screen. So when you start talking about adding an additional level of complexity like that, all of a sudden latency through the Windows system becomes a real problem. And this notion of adding more computation to a system which is already computationally constrained is a real problem. The other thing we talked about was just using render to hide the displays, changing the extension so that the desktop couldn't see the display. Again, no kernel changes required, few X changes required. Gets rid of the need to change the desktop environments. That was nice. But again, if we're displaying the image through the X window system, all of a sudden we've got all the latencies involved in having another process in the chain. We could create a meta display server to manage all the outputs so that the Windows system and the head-mounted display would send their outputs down to the meta display server and it would figure out what to do with the kernel. Well, that gets rid of a lot of the latency problems inherent in having a Windows system involved. You don't have any compositing system going on, so you're not blending images together. You still have another application involved, so it sounds better. No kernel changes required. It largely addresses the latency issue, but it still has another process involved. So you have more context switches. And in our new Spectre world, context switches are getting even more expensive. So we fortunately got to avoid that. So the change that Dave and I came up with that we thought was going to work pretty well was to change the kernel, because we can hack the kernel. It's free software. It's awesome. We can change anything we need to do. To change the kernel to actually say, okay, this application gets to talk to this monitor, and this application can talk to this monitor. And that way we can have this application driving the Windows system and this application driving the HMD through the kernel. And that way they don't interact at all in the display process. This hides the displays from the Windows system nicely, gets rid of our latency problems. We don't have to change desktop environments. We do have to change X in the kernel, but hey, Dave and I are kernel hackers and we're both X hackers. So that was like, hey, this is right in our wheelhouse. We know how to change these parts of the system. So the goal here, of course, is to get X or any other Windows system out of the picture, right? It's not helping. I don't need management of geometry on the display. All the input devices are these custom HMD input devices, so I don't need to multiplex those to different demultiplex those to multiple applications. So the Windows system is really just a problem here, so we're going to get it out of the way. We're going to make the HMD app display directly to the device, right? So when you talk about the DRM environment, which is the way that we do 3D graphics in the Linux environment, the DRM client already talks directly to the kernel to do all of its rendering. It's called the Direct Rendering Manager for a reason. Applications don't talk to the Windows system when they want to do 3D graphics. They talk to the kernel. So I've already got a kernel file descriptor, right? I already am talking to the device. All I need to do is make that file descriptor more capable, or give me another file descriptor that can do the additional things that I need. So all I need to do is add the ability, a direct mode setting ability to this application. But of course, the mode setting stuff is a privileged operation. You wouldn't want any random application coming along and stealing and changing modes and like putting up a little window that says, hey, your screen is locked. Would you type your password for me? Oh, I didn't mean that password. I meant your Facebook password. It's like, why do I need my Facebook password to unlock my screen? So we don't want applications coming in and hijacking your screens. And so that's why access to the display is a privileged operation, usually mediated through the Windows system. So we didn't want to just open up access to the displays to the world. There is a particular vendor which did this way. They do a closed source kernel driver. We decided that we needed to retain our secure environment. So we have a mechanism that pulls the display out of the Windows system and hands it to the HMD application. And this also retains a little bit of control so that when an application crashes, we wanted the Windows system to be able to find out about that. Oh, your application crashed. And yeah, it left the display in kind of a mess. So we want X to be able to kind of pick up the pieces and put the display back together and be able to use it for the desktop again if you want to do that, or hand it back to the HMD application. So now we have a mechanism for providing the display to the HMD, and we have a mechanism for the system to recover when an application crashes. Because how many of you have ever played a game and had it crash? Yeah. And let me tell you, when you're doing beta application development for Valve, their games, when they ship them, are way more stable than when they're under development. I know, just like any other system. Okay, so what we did is we came up with this notion of a lease. It's a kind of a cheesy metaphor. You got to come up with a metaphor for everything, and naming is hard. So we came up with this notion that you're not going to own the output. It's not really yours to go in. So if like you put nails in the wall, you have to patch them up before you leave, or you have to pay somebody to come and patch them up when you leave. You're not allowed to put new carpet down without asking permission. So in a similar way, you have a limited access to this resource for a limited amount of time. For the time that your application runs, you can't keep using it. So the lessor, the Windows system here, owns all of the resources and controls them all in perpetuity. And what it does, though, is it gives you a right to use that resource, so that it promises that it's not going to come in. Just like your landlord has to call you a day before when he wants to come in and inspect the property. In the same way, the X server promises not to come in and bug the application when it's busy displaying stuff. So, the metaphor went pretty well. And the lessee, of course, is this VR application. It gets to do mode setting on that output and do presentation on that output while it's running. It can even do DPMS on and off. So you can turn the monitor on and off and do power saving if you like. And then when the lease terminates, which is to say when the application exits, or when the user says, hey, that application is doing something bad, please stop it from displaying. So you can either the application can terminate or the Windows system can take the lease back. Then the lessor gets the display back and it can clean up. Okay, hello. Awesome. Oh, here we go. Okay, as usual, when you're doing new stuff in the kernel, you get sidelined. This is, I think any software development is a sequence of yak shaving exercises. Here's one. We had this horrible API for monitoring v-blanks in the kernel. So what you want to do with the v-blank is you want to find out what's the current frame count, and please send me an event when you get to this frame count. And that lets you do things synchronized to the refresh of the monitor. So every time the monitor displays another frame, it might be able to send you an event. The little counter increments, and it might send you an event. The current API was a single I/O control, which did 3 different things depending on the parameters. Well, that's a terrible interface. In particular, for the usage that I needed, it had a couple of really bad limitations. The first limitation was it had a 32-bit counter, which means that after a couple of years, that counter wraps, which means I can't treat the counter value as unique. For all practical purposes, yeah, a couple of years is a long, long time, and I should be able to treat it as unique. But having experience in this environment, I've had users say, I ran my X application for 4.5 years, and after 4.5 years, it stopped working. Can you tell me why? It's like, that's a long test debug cycle. So I'm really hesitant to put any counter system like this that has this kind of wrapping behavior.